Hey, you guys. This is the first lecture on our unit over the beginning of the universe, the Big Bang Theory, those sorts of things. We're going to be learning about how our galaxy is structured, where our galaxy came from, and our universe came from. But in order to understand how we know these things that we know today, we have to understand something about light. Now, we can ask the question, well, what do you think light is? Is light kind of an energy that comes from things, or is it little tiny particles of something? Is it waves of something that comes from a light bulb? Is it something else? Well, we can actually figure this out. And we figured this out actually back in the 1800s by a very simple experiment called the double slit experiment. You can look that up sometime if you want to. Now, what the double slit experiment demonstrates is that light is best thought of as a wave, kind of like the same sort of waves that move through the air to produce sound, or the same sort of waves that move through water to produce uh, tsunamis or tidal waves or something like that. Now, we can ask the question, what does it actually mean for light to be a wave? And this actually relates directly to the way that you see the world. Now, not all light has the same wavelength. And so, actually, the difference in wavelengths contribute very intimately to your experience. What is a wavelength, first of all? A wavelength is a distance from the top of one wave to the top of the next wave. Now, here's the thing. Light, just like anything else or any other wave, has a wavelength. And there is a way that your body, your person, perceives these differences in wavelength. These different wavelengths of light are interpreted by your brain as color. So, for example, if light has a longer wavelength, if the waves are kind of more stretched out, then that light is perceived by your brain to be red. On the other hand, if it has a shorter wavelength, so if the waves are more squeezed together, then your brain interprets that light as being blue. So what we see here is that color is not really something that exists out there in the world, but color is a way that your brain interprets different wavelengths of light that are bouncing around in the world around you. Here we have a wave, and the length from the top of one wave to the top of the next wave, or the length from the bottom of a wave to the bottom of the next wave, is known as the wavelength. And down here we have what's called the electromagnetic spectrum. It's showing different wavelengths of light as we move from short wavelengths down here to long wavelengths over here. And what you can see is that as we make the wavelengths of light shorter and shorter and shorter, the light becomes more blue or purplish. And then as we stretch out those light waves and we make their wavelengths bigger, that light actually is what's seen by us as red light. Now, this is important for a couple of reasons, because it has to do with we use light to tell a lot of things about the universe. At the very basic level, we have telescopes, and telescopes bring in light and put them into our eyes so that we can see things that are far away. So, but there's an important thing about light and about all waves that happens that we have to understand. If you've ever heard a train pass by you, it makes a sound like this. It goes, right? And you notice that, I know it's a funny sound, but you notice that I started at a high pitch, and then as the train goes by, the train gets a lower pitch. It goes, right, like that. And so what that is called is the Doppler effect. And what happens during the Doppler effect is that the sound waves in front of the train, as it's approaching you, the sound waves in front of the train are getting squeezed together, and that makes it a higher pitched. But then when the train passes by you, the sound waves coming from the train are stretched out and the wavelength increases. And so that makes it sound a lower pitch. So we can apply this same thing to objects in the universe that are moving either toward or away from us. Objects that are moving toward us, the light in front of them, the wavelength is getting. Sorry, we're going to start with things that are moving away from us. Things that are moving away from us, their light is being stretched out, and so their light appears more red. Now, if something is moving towards us, like a star or a comet or something like that, the light waves in front of it are being squeezed together, and that makes the light appear more blue. So here is a kind of an example of the Doppler effect. Here we have a moving object and we have waves coming from it. And so in front of the object, the waves are getting squeezed closer together, but behind the object, the waves are getting spread out. And so the way that that happens with light is that if a star is moving away from the Earth, its light appears red-shifted. But if that same star starts moving towards the Earth, then its light becomes more blue shifted. So we can actually tell how far away or how quickly something is moving towards or away from us based on its red shift. If it's moving away from us very quickly, its light will look more red. If it's moving towards us very quickly, its light will look more blue. We are going to apply that later on to how we use the Doppler effect to figure things out about the universe.